Thank you very much, and it's wonderful to be back here at Knutsford SciBar. So this is cosmic rays. For the last half hour or more, we've been looking at cosmic rays in this little cloud chamber that I built, and instructions are on the front desk if anybody wants to build one for themselves. We'll be coming back to the cloud chamber and other detectors in due course. So in this talk, I'm going to give a little bit of an introduction and then talk not immediately about cosmic rays. I'm going to start with terrestrial radiation, background radiation from the Earth, to put into context radiation from somewhere else other than the Earth, cosmic radiation, which has been with us, or at least, of course, it's been with us forever, but we've known about it for the last 100 years or so. I'll be saying a little bit about detectors and what are the sources of cosmic rays. Not only how do we detect them here on Earth, but where did these rays come from in the first place? And then I'll summarize right at the end. So firstly, I have to tell you, because I'm legally obliged to do so, I have some radioactive samples on the front bench, and the SciBar lawyers insist that I tell you that there is no risk to any member of the audience. Assuming you don't come up here, take one and eat it, then everything will be fine. I've got a couple of detectors on the front bench. Some of you may have already seen them. I've got a Geiger-Müller detector, otherwise known as the Geiger counter, and I've got a cloud chamber. And we're going to be using those detectors in due course, dipping in and out of them in between the PowerPoint slides. So firstly, we can ask, what's that clicking? So a Geiger counter, well, as a physicist, we really shouldn't call them Geiger counters. We should give them their correct name of Geiger-Müller detectors. But that's being a little bit pedantic, so forget Geiger-Müller detectors. Let's just call it a Geiger counter. Geiger counters give us a click whenever a subatomic particle passes through the detector. Where did that particle come from? Well, it might have come from an atom that happened to be floating around in this room, a radioactive atom which spat out a particle and ended up going through the Geiger counter detector. Or it might even have resulted from particles coming out of, let's say, possibly, a supernova that went off a long time ago in a galaxy far, far away. The click doesn't tell us. The click is just something has passed through the detector. A Geiger counter is precisely what it sounds like, a device for counting how many particles have passed through. And sometimes it really matters whether it's 1 per second or 1,000,000 per second, but it doesn't tell you what type of particle. For that, we need something else. So let's start by talking about background radiation, terrestrial radioactivity. So we have to remember that radiation is around us all the time. You've lived with it all of your life, and it's not necessarily anything that you need to be worried about. Natural radiation that is not man-made far outweighs any contribution from man-made radiation. So before dealing with cosmic rays, let's just take a little dip into terrestrial radiation. We have to remind ourselves that planet Earth is radioactive. It's nothing to do with mankind. It's radioactive because it was radioactive when it was made 4.54 billion years ago, and it's still radioactive now. That's a consequence of the elements in the periodic table that make up the Earth. So we can remind ourselves that there's 92 or so elements, plus a few that we've made ourselves. And we have to realize that atoms come in a sense, two varieties. That's a bit of an oversimplification, but that's perhaps the best way of looking at it. We either have stable atoms, in other words, once you've made an atom, that atom remains essentially unchanged for all time. And there's another bunch of atoms that want to be something else. They're unstable. They decay. That's the way physicists talk. It doesn't mean they go moldy. It means they change into something else. Some atoms change from one element in the periodic table to a different element in the periodic table. So physicists talk about an atom decaying into other elements. And in the process, the nucleus of the atom will spit out a charged particle, or might spit out a charged particle, and that's contributing to the clicks in the background. So we can visualize what's going on. We're going to take one particular example of all the possible radioactive elements that are in the periodic table. I've just chosen one, and I've chosen uranium. Now, when it comes to looking at uranium, we have a number of different choices. What I'm going to do is to switch from the cloud chamber to this little piece of glass here. It's not particularly little, it's a rather large piece of glass. It's a piece of glass that's been doped with uranium. There's definitely radioactive uranium in there. We can tell because if we just flick to the Geiger counter and I bring it up to the detector, you can see there's far more coming off this glass. Not enough to be worried about, but there's more coming off this glass than there is just in the normal background. Why do people put uranium into glass? Well, it's nothing to do with the radioactivity. They just think it looks pretty. If I come back to the box in just a second, people put uranium in glass because it has a particular property. If you shine ultraviolet on it, it fluoresces like mad. And so it's rather pretty. If you put this in a cabinet and have some UV LEDs on it, it glows. And for the benefit of anybody watching the video, what I've just done is to demonstrate that under UV, uranium fluoresces like mad. But that particular piece of glass, although it's rather pretty, is way too big to put into the cloud chamber. So what I'm going to do is to put a much smaller radioactive sample into the cloud chamber so you can see what's going on. So rather than being a few centimeters across, this particular piece of a uranium mineral is only a few millimeters in size. So you can see just about at the end of the tweezers there, a few millimeters of radioactive sample. If I bring it up to the detector, quite definitely radioactive. Yes, no doubt about that. Let me switch the speaker off because that gets annoying after a little while. If we come back to the cloud chamber, we know the cloud chamber shows us the passage of charged particles. We've just seen some ones that are coming from cosmic rays. But what would happen if I put a radioactive sample in the cloud chamber? To do that, I have to disturb the cloud chamber. The cloud chamber is quite happily at the moment having clouds of alcohol generated. I'm going to try and put the sample in by making the minimum disturbance possible. And that was perhaps too much, but there we go. So now we have a radioactive sample sitting in the middle of the cloud chamber. We can still see the drizzle coming down, but we can't see anything else happening. Let me just center that up slightly and zoom in to make it a little easier for you to see what's going on. Zoom, zoom, zoom. Okay, at this point, I have to waffle for quite a while until the cloud chamber settles down again. I've disturbed the cloud chamber, so the original vapor being generated at the top and condensing at the bottom, producing a sort of cloud through which we can see tracks generated in the same sort of way that an aircraft traveling through the upper atmosphere, where water is just at the point of wanting to condense. If a plane flies through the upper atmosphere where it's very cold, then the passage of the aircraft can actually trigger the formation of water droplets, and so the aircraft leaves a contrail. It's the same sort of idea, not quite the same physics, but the same sort of idea. So once the cloud chamber has had a chance to stabilize, which might take a minute or two, we should start to see the radioactivity of this sample, because it will be producing charged particles which hopefully are visible, easily distinguishable from cosmic rays, because cosmic rays will just go at random through the entire plate that we're looking at. But of course, if they're being generated by this sample, everybody see that one? Yeah. Yep. So once the cloud chamber has settled, we're now starting to see something being emitted by this sample. Let's just wait for a few seconds so we get a good idea of what's going on. Remember, in a cloud chamber, the cloud is effectively a layer above the cold plate. So any particles emitted by this lump of uranium, it's a uranium mineral, doesn't really matter which one, it's called studite, but it doesn't matter. The uranium is producing particles. If they go up, we don't see them. If they go down, we don't see them. If we go sideways, then we have a chance of seeing them. And you can already see there's quite a few particles coming out. And you might notice that there are different types of streaks, different types of tracks coming out of the radioactive sample. There's at least two types. Those that are very distinct and narrow and bright, like that one and those two, and others that are more ghostly, more diffuse. So even without knowing anything of the physics, just by looking at the tracks, we might say there appears to be two families of particles coming out of this particular rock sample. So let's just zoom out again and go back to our PowerPoint. So just in case it didn't work, I have total faith in this cloud chamber, but just in case, this is the Blue Peter version of, this is what I saw on my kitchen table with a different lump of material, a much bigger one, but again, you can see different tracks coming out. After a minute or so, I took that video and I added up all the tracks. I composited all the tracks that I could see, and that's what you get after a minute or so. Notice that we have quite a few tracks that are very narrow and relatively straight, perhaps a little bit wiggly. But we also have a whole set of family of tracks which are very diffuse, much fatter, and generally speaking, much fainter. So we have a whole ghostly set of tracks coming out, and we have a whole set of relatively narrow tracks. So we might deduce there are two types of particles coming out of radioactive materials like this. So it's clearly emitting something, but we can ask ourselves, as indeed people did 100 years ago when radioactivity was first discovered, what is it that we're actually looking at? It took a little bit of work to work this out, but 100 or so years ago, when people were studying radioactivity and the nature of the atom and the existence of the atomic nucleus, we now know that an atom, it doesn't really look like this, but this is a good enough model to use. An atom is effectively a positively charged nucleus with lots of negatively charged electrons buzzing around it. And it didn't take too long to realize that when it comes to radioactive decay, when it comes to one element changing into another, it's only the nucleus that matters. You can take an atom and you can take electrons away and you can add electrons to an atom. It doesn't change the nature of the atom. If you take a uranium atom and add electrons or remove electrons, it's still uranium. But if the atom is going to change, then changes must happen within the nucleus, and it's the nucleus that's responsible for radioactive decay. I'm not going to go through all the details, but just to give you a flavor, if we had a very heavy nucleus with lots of protons and neutrons in there, the protons are positively charged, neutrons are neutrally charged. If that nucleus did want to change, it could change in principle in a number of different ways. For instance, it could spit out one of its protons, in which case it changes to a different element. Alternatively, it might spit out one of its neutrons if it doesn't like the balance of protons to neutrons within the nucleus. It might spit out a combination of those two. In particular, it might spit out two protons and two neutrons because that's a very stable structure. It's also known as the nucleus of helium, but it's also, in this context, called an alpha particle. So that just happens to be a very stable structure. Nature likes to make alpha particles, two protons and two neutrons. A nucleus might also spit out a positron, which is an antimatter equivalent of an electron. In other words, an electron or its antimatter equivalent. So a negatively charged electron or a positively charged electron, more accurately called a positron. That might be something it spits out. And it's also possible that it doesn't spit out any charged particles at all. It might emit an electromagnetic wave, for instance, a gamma ray. So there's lots of ways that a nucleus can change. I'm not going to go through all of the details of that because we're only really interested in 2 or 3 examples, so-called alpha, beta, and gamma radiation. These are the ones that you learn at school, and these are the ones that are arguably most important in this context. An alpha particle or an alpha ray, bear in mind that we're not making any distinction between rays and particles. In the early days, they weren't sure whether these things were rays like rays of light or whether they were particles in the sense that we understand them today. So the word alpha particle and alpha ray, they've got mixed together to the point where it doesn't really matter which label you use. It's the same thing. So an alpha particle is the nucleus of a helium atom. It's made up of 2 protons and 2 neutrons. It's a very stable structure. Heavy nuclei in particular like to make these things. They can't travel far through matter. For instance, they can't get through the glass of a cloud chamber. Beta rays, we later came to realize that beta rays are simply electrons, or possibly the antimatter equivalent of electrons, depending on which charge they have. Electrons are much lighter than alpha particles, therefore they tend to scatter more, and in the cloud chamber they produce much more erratic zigzag tracks. Generally speaking, they can travel a little further through matter than alphas can. I'm not going to be talking much about gammas. Gammas are electromagnetic radiation. They are not charged particles. Cloud chambers are designed to see charged particles. So gammas do not produce tracks in a cloud chamber. They might produce a click in a Geiger counter, but we can't see them in a cloud chamber. So that's the alphas and betas and gammas. And if we go back to our video, that explains why we're getting two different types. We're not seeing the gammas, but we are seeing alphas and betas. Betas are the very narrow tracks that we can see every once in a while. Alphas are more massive. They're more like bulldozers. As they go through the cloud chamber, they tend to produce a much fatter track. They don't travel that far, but they do produce quite a lot of damage as they go along, and they produce a very fat track. So the narrow ones are the electrons, the betas. The fuzzier, broader, more ghostly tracks are the alphas. So again, if we go back to, yes, I'll go back to the PowerPoint, but whilst we're looking at the video, again, I will take the sample out because later I want to come back to cosmic rays, so we are done with this. So I want to take that one out and let the cloud chamber recover again. So that little bit of uranium has done its job. So again, this is just the same video, but now we can identify, yes, there are two types of tracks, and they are in fact the alphas and betas. These are quite definitely electrons, the very narrow ones, and these bulldozers with a very fat track are quite definitely alpha particles. So you can see the power of a cloud chamber is we can tell there are differences, and if we apply the physics we learn by various experiments, we can start to identify which particular track is which. Before I move on and talk about cosmics per se, let me just make another couple of definitions. Isotopes are the labels we give to cousins of atoms of the same type. In other words, for instance, a carbon atom has 6 protons in the nucleus. That's a matter of definition. If you take any nucleus and it has 6 protons in it, then that is a nucleus of carbon, regardless of what other number of neutrons it has. If it's 6, it's carbon. That's just the label we use for a nucleus with 6 protons. So all carbon has 6 protons, but the number of neutrons may vary. For instance, a nucleus might have 6 protons and 6 neutrons. 6 protons and 6 neutrons means we've got 12 of these objects in the nucleus, which is why we call that particular isotope, this particular cousin of carbon, we call that carbon-12, and that's a stable atom. An awful lot of the carbon in your body is carbon-12. But there are other types of carbon. There is a particular isotope of carbon called carbon-14. It has the same 6 protons in the nucleus because it's carbon, but it has 8 neutrons. So 6 plus 8 is 14, so we call this particular isotope carbon-14. That's the one that's used in radioactive dating. It doesn't last very long, it only lasts for a few thousand years. So, okay, that's plenty for us in terms of our lifetime, but if you wanted to date a tree and figure out whether or not it lived 1,000 years ago or 10,000 years ago, you can look at how much carbon-14 is in there compared to the amount of carbon-12, and you can use that to date organic material. So isotopes are just cousins, effectively with different numbers of neutrons, but the same number of protons. Potassium has some interesting isotopes, one of which I'll come to in a moment, but perhaps you don't realize that potassium is one of the most abundant radioactive elements. Everybody talks about uranium or man-made elements like plutonium, but in fact, most of the radioactive material you're ever going to come into contact with is actually potassium. There's an awful lot of it in your body. There's so much potassium in your body that there's probably 4,000 atoms decaying every second in everybody's body. That sounds like a lot, but of course it's tiny because the number of atoms in your body is a million, I don't know. There's an awful lot of atoms in your body, so 4,000 per second you'll never even notice. So it sounds a lot, but it isn't. It's one of the largest contributions, though, to natural radiation. Thorium is actually more abundant than uranium, and uranium is probably more abundant than you think. People seem to think uranium must be very rare because it's only used in bombs and nuclear reactors and things. No, there's an awful lot of uranium around in the world. Uranium is actually 500 times more abundant than gold. It's just more difficult to get out of the ground. Gold is easy to get out of the ground because it forms nuggets. Uranium has to be dug out of the ground as uranium ore and then processed, so it's more tricky. So 3 parts per million, again, doesn't sound much, but it's huge compared to precious metals. In the Earth's core, we have a lot of these radioactive elements, potassium and thorium and uranium in the Earth's core. They've been there since the Earth was made, and they are slowly decaying away, releasing energy in the form of these energetic particles, and that is keeping the core hot, and it's keeping the core molten. The Earth's core is hot, nothing to do with radiation from the sun. The Earth's core is molten because of the radioactive elements that are in there. So if you've got a whole load of molten metal spinning in the inside of the Earth, that's the dynamo that gives us a magnetic field. So we have a magnetic field because of the radioactive decay of these elements. So it's rather ironic that radioactive decay gives us a magnetic field, and the magnetic field helps protect us from cosmic rays. It's a sort of natural circle of life, if you like. So as we will see shortly, it doesn't protect us from all cosmic rays. There's an awful lot of radiation out there, some of which is protected by the Earth's field. And of course, we know that the Earth's field particles will tend to funnel into the poles and give us aurora every once in a while. Just as an aside, I've already mentioned the fact that some charged particles spat out by nuclei won't necessarily be the familiar ones we're used to, like electrons. It might be the antimatter equivalent of those. For instance, potassium-40, one of the isotopes of potassium, it's not very abundant in the sense that there's an awful lot of potassium, only a small percentage is potassium-40, but that potassium-40 isotope actually spits out beta plus radiation. Electrons are negatively charged, so beta plus means it's the antimatter equivalent of the electron. So yes, you are emitting antimatter because you have got some potassium in your body. Any food that's rich in potassium will be spitting out quite a bit of antimatter. Brazil nuts, bananas will produce a lot of antimatter. And that gave rise to the somewhat whimsical unit of, why don't we have a banana equivalent dose? If we're talking about radioactive doses, rather than talk about silly physics units that nobody understands, why don't we talk about the dose equivalent to how many bananas is that equivalent to? When you're talking about low levels of radiation, maybe that's a better way of talking about radiation dose than talking about the huge numbers that might come out if you've been exposed to very high doses of radiation. So for instance, if eating one banana gives you one banana equivalent dose, then you can say, well, how much are we receiving? Every day of our lives, we receive a dose of radiation from cosmic rays. Doesn't really make a lot of difference if we're inside or outside. It would only make a difference if we went a mile underground to shelter from cosmic rays. So in terms of the banana equivalent dose, how much is a dose of cosmic rays that everybody gets every day? The equivalent is approximately 2 hands of bananas. So in other words, you're actually getting the equivalent of 10 or 12 bananas. It would actually be slightly higher if you fly a lot, because if you fly a lot, you're above the atmosphere, you're closer to the source of the cosmic rays, and you'll actually receive a higher dose. That's why you've got to watch. Airline pilots have to be careful how many hours they fly, because they're spending a lot of time at altitude. They have to worry about exactly what their dose is from cosmic rays. As far as I know, airline pilots don't get calibrated in bananas, but they still need to keep an eye on it. And finally, as I mentioned before I started the talk, but I'll say it again, not all radioactive elements are found in solid form, like a little lump of uranium that I've been showing and putting into the cloud chamber. Some radioactive material is in the form of gas. So radon is the most common radioactive gas. It's formed by the radioactive decay of various elements, including uranium, that occurs in essentially all rocks in tiny amounts. So in other words, there's probably some uranium under our feet, or at least under the next floor under our feet. It especially occurs in granite. Granite has a lot of uranium. Uranium produces a lot of radon, and therefore you might get radon gas forming if you live in an area with a lot of granite. So that tends to be the Pennines or Cambria or the southwest of England. In particular, Cornwall and Devon, because of the granite there, an awful lot of uranium in the ground, an awful lot of radon is produced. Here in Cheshire, you see we're at the lower end of this particular map. Red is high, pale blue is low, so there's not much going on here. Radon gas emits alpha particles. Therefore, if we ever see an alpha particle inside our cloud chamber, it can't have got through the glass because alpha particles don't travel that far through solid material. They travel through air a few centimeters, but they don't travel through glass very well. So if we ever see an alpha particle in the cloud chamber, it's almost certainly come because there is a little bit of radon in the cloud chamber. There's radon in the cloud chamber because there is radon in this room. How much? I would estimate, based on this map, that the amount of radon in this room is approximately 1 billion atoms, which again sounds a lot, but it isn't, because every cubic centimeter of this room contains a huge amount of nitrogen and oxygen and only a tiny, tiny, tiny amount of radon. So that was a background trying to understand alpha and beta radiation and naturally occurring terrestrial radiation before we get stuck into cosmic rays. So in terms of cosmic rays, the pioneers of radioactivity and radiation, I would argue, are these three individuals. They were the big contributors in these decades around the turn of the late 1800s, early 1900s. I'm sure everybody recognizes Marie Curie in the middle there. Perhaps some of you know Henri Becquerel, who discovered radioactivity. He had some photographic plates which were sealed from light, and yet they still fogged if he put a bit of uranium into the same drawer as the drawer in which he stored the photographic plates. So he realized that uranium produced something other than light that was getting through the protective covers and fogging his plates. So he discovered radioactivity. Marie Curie refined various elements. Later we came to know them as polonium, radon, radium, etc. Perhaps you haven't heard of Victor Hess, but he's a key player in what we want to say about cosmic rays. It was known around the late 1800s and early 1900s that something was affecting the radiation measurements that these people were trying to make. They used what we call an electroscope, a gold leaf electroscope. You know that if you charge your hair by running a comb through it, your hair tends to stick up a little bit because like charges will repel each other. So this is a gold leaf, 2 gold leaves inside a protective bell jar just to stop any air currents affecting them. If you charge this up, if they're the same charge, they'll repel each other and the 2 gold leaves will separate. So you can tell when you've got electric charge inside that bell jar because the gold leaves will separate. If you lose that charge somehow, those gold leaves will collapse and come back together again. And it was noticed that whenever you charged one of these things up, if you left them alone, they discharged. Something was either adding or taking away some charge from this particular type of radiation detector, or charge detector, I suppose I should say. So if they lost their charge, they figured there's some background radiation. There is some flux of charged particles that's affecting our electroscopes and making those gold leaves collapse. But where's it coming from? Is it coming from above or is it coming from below? In other words, is it coming from the Earth or is it coming from the sky? Well, in 1910, Theodore Wolff said, well, let's do an experiment. Let's take an electroscope and measure the radiation levels on the ground, and then let's take it to the top of the Eiffel Tower and see if the radiation levels go up or if the radiation levels go down. Great idea. Unfortunately, the result wasn't very convincing. It sort of changed a little bit, but it was very difficult to get an accurate register of whether or not it was going up or going down. But it seemed to decrease, but decreased by far less than was expected if it was coming only from the ground. So they thought, do we have complications? Is it possible that the Eiffel Tower is radioactive? Not a silly thing to say, because the Eiffel Tower is made of iron. Iron is dug out of the ground. The ground is radioactive, so maybe the Eiffel Tower is radioactive. But also they knew about radon, so they knew the atmosphere was mildly radioactive. So is it possible that their results were being affected by the atmosphere around them? So it was inconclusive. That's where Hess comes in. To resolve the question of where is this background radiation coming from, Hess said the Eiffel Tower just isn't high enough. A few hundred meters is not enough to tell whether it's coming from below or coming from above. So he said, how do we go higher than the highest thing around? Well, you start using balloons. So he said, right, okay, I'll make sure I can design a detector. He sort of modified the electroscope to allow him to measure radiation levels as a function of how high he went in his balloon. And in 1911, 1912, he took a number of different flights to see whether or not the radiation levels change when you go not just hundreds of meters, but when you go thousands of meters into the air. So in 1911, he ascended to 1,000 meters, And he said, well, the radiation levels sort of changed a bit, but it's not really obvious. It didn't seem to change. So no surprise that the Eiffel Tower was inconclusive, because even at 1,000 meters, it's not clear whether the radiation levels are changing or not. But then in 1912, he took a flight to 5,000 meters, and there he saw the radiation levels just increase dramatically. And it was absolutely obvious that at 5,000 meters, you're a long way from the ground, the radiation levels are going through the roof. It is obvious that the radiation that they've been measuring is coming from above, not from below. So the second question is, now that we know it's above, not below, that's been conclusively indicated by Hess, the question is this radiation coming from above? Is it coming from the sun? So what's the choice? One option is to say, well, we're going to take a hot air balloon flight and we're going to do it at night. And we're going to go up and we can't see what we're doing, we can't see where we're going, and we can't see where we're going to land. Nobody wanted that particular job. So what's the alternative? If you want to know whether the sun is a source of cosmic rays but you don't want to fly at night, what's the option? Hess had a fantastic idea. You fly on the day of a solar eclipse. Brilliant. You go up, you measure the radiation. When the moon covers the sun, it's a reasonable assumption that the moon is such a big object, it's going to block any radiation from the sun. It certainly blocks the light. Let's assume it blocks this other stuff as well. So you see if the radiation levels plummet during a solar eclipse, telling you the radiation comes from the sun. No, radiation levels did not change during the eclipse. So the sun is not a source of cosmic radiation. Perhaps a tiny fraction of the particles that we measure are from the sun, but it's not the prime source of cosmic radiation. In 1936, Hess was awarded the Nobel Prize in Physics for the discovery of cosmic radiation. It was his balloon flights that basically determined, yes, cosmic radiation exists, it's definitely cosmic, and it doesn't appear from the sun, so it's coming from somewhere else in the galaxy or beyond. We now have this idea. This is an artist's impression of what we think is going on. Charged particles are hurtling around the galaxy, and when they hit the atmosphere, they produce a cascade, a shower, a so-called air shower, because an incoming energetic particle basically hits something in the atmosphere, maybe oxygen or nitrogen atoms, and that produces more secondary particles, which then hit more atoms, which then hit more atoms, just like an avalanche. So that's what we think is actually going on, determined by a number of different experiments, which I'll come to when I talk about the detectors. But let's have a think about what's actually going on in here. That's far too complicated. That might be realistic, but it's a bit complicated. That's a simpler version of what's going on. An incoming so-called primary cosmic ray that's coming from somewhere that we haven't yet determined, it hits something and produces secondary particles, some of which make it to ground level. So a primary incoming ray produces secondary rays or secondary particles, which then travel through the rest of the atmosphere and may or may not reach ground level. At each level of the cascade, the energy of the incoming particle is shared. So in other words, if the incoming particle ends up producing 4, then those 4 particles share the incoming energy. Not necessarily equally, not necessarily a quarter each, but the energy of each of the particles coming down in this cascade, if you could add them all up, tells you what the energy of the incoming particle originally was. And it might be that, remember this is a rather simplified version of the diagram here, one primary incoming particle, if it's energetic enough, might produce not hundreds, it might produce millions of secondary particles down at ground level if that incoming primary particle has enough energy. What are the sorts of particles that are produced? Well, they are not necessarily the particles that we are used to. We're used to being made of atoms, and atoms are made of protons and neutrons and electrons. Well, yes, some of these particles might be the familiar particles that we're used to because we know that they are constituents of atoms. But it was also realized fairly early on that some of these particles that are generated by cosmic rays are not the particles that make up us or anything else that we know of. Some of these particles are new. In other words, they don't make atoms, they might be unstable, they might only live for a tiny fraction of a second. One of the most common particles that are generated in these so-called air showers is called a muon. A muon is sort of like an electron, but much heavier. It's 200 times heavier than an electron, but again, it comes as a positive or a negative charge. But muons have nothing whatsoever to do with making atoms, mainly because they're unstable. They only live for a couple of microseconds. So if we see a muon in this chamber, it was born a few microseconds ago and will die, will decay into something else very soon after passing through the chamber. So a muon has no part to play in making atoms. It will only live for about 2 microseconds, and if you work out how long it takes to get from the upper atmosphere down to the ground level, even at the speed of light, it takes more than 2 microseconds. But here, Einstein helps us because Einstein tells us that time slows down for the muon because it's traveling almost at the speed of light, and therefore it will reach ground level, even though a simple calculation of 2 microseconds only gets you a few hundred meters. It will indeed get you tens of kilometers down to the ground. And that's what it would look like in the cloud chamber. There's a picture I took a long time ago. I bumped the contrast up to make it a little clearer. Rather than have a gray background, it's got a black background. But there's a muon traveling in roughly a straight line, leaving a trail of alcohol droplets behind it. We can tell that's a muon, not an electron, because an electron will be much more ragged and jagged and zigzag as it goes through the cloud chamber because it's a lot lighter. The muon is heavy, so it tends to go in a straight line. And that particular particle was probably traveling fairly close to the speed of light when it went through the cloud chamber. So we can see these particles at ground level, these secondary particles, but what about the primaries? We can tell by looking at the tracks that in a secondary particle family, we see electrons, we see muons, we see some protons. Alphas, remember, are nothing to do with cosmic rays. But it took us quite a while to figure out, yes, but what is it that's coming in at the top? What is it that's hitting the atmosphere that's producing this air shower? What's producing this cascade? It took us a while to figure out that the primary particles, the ones that create the showers in the first place, most of them are protons. In other words, they're hydrogen with the electrons stripped away and just leaving us with a single proton. 90% of cosmic rays are just the nuclei of hydrogen atoms. 9% are the nucleus of helium atoms. Remember, the 2 neutrons, 2 protons, that's the alpha particle. So we can call them protons and alpha particles, or if you wish, you can call them the nucleus of hydrogen, the nucleus of helium. That's 90% plus 9%. What's left? Well, the remaining 1% is everything else. And it looks like everything else is lots and lots and lots of even heavier nuclei. Which atoms? Well, essentially all of them. Lithium, beryllium, boron, carbon, nitrogen, oxygen, all the elements that make up the solar system appear to be there in cosmic rays in smaller and smaller numbers. The most abundant ones are just hydrogen, some alphas, and tiny amounts of all the other nuclei in the periodic table appear to be making up cosmic rays. So how is it that we detect these things? How do we detect them either as secondary at the ground level or up there as primary? Well, one way is using what we've already seen, a Geiger-Müller detector. What's actually going on inside that detector that we used for the uranium glass and the uranium mineral? Well, a Geiger-Müller detector is relatively straightforward. It's a cylinder with a high voltage down the middle, and radiation coming in will ionize the gas inside. The gas inside is some inert gas like helium or argon or something like that. Any radiation coming in will ionize the gas, and then the positive charge goes one way and negative charge goes the other because we've applied a voltage to this particular detector, usually at least a few hundred volts, maybe 1,000 volts. And if we simply, after that ionization, simply allow the plus and minus charges to go to these electrodes, we simply measure the current. And every time we get a blip in the current, this yellow box simply turns that into a click so we can hear what's actually going on, and obviously indicates on the rate meter how many we've got per second. So it's relatively straightforward. The cloud chamber was invented back in 1911 by a Scotsman. On seeing the Brocken spectre, allegedly from the top of Ben Nevis back in, when was it, 1894, Charles Wilson said, that's an amazing phenomena. If you've got moist air and the sun behind you, you get some very interesting optical effects. But he didn't want to set up a laboratory on the top of Ben Nevis to study these things. He figured, I want to bring the clouds down to the laboratory rather than take the laboratory up to the top of Ben Nevis to study these things. So he basically said, how can I make a cloud in a jar? So he perfected the cloud chamber back in 1911. It looks a bit odd because he didn't have modern technology. He had to generate the clouds by expanding volumes of gas to make the water condense. But after making cloud chambers back in 1911 or so, it wasn't long before he realized whenever he made a cloud, he would occasionally see these streaks, these lines, these tracks that came through his cloud chamber. And it didn't take him that long to realize he was looking at radiation, charged particles that were moving through his cloud chamber. So charged particles left visible tracks. And this was revolutionary because that meant that particle physicists who were trying to understand what are atoms made of, can we understand the makeup of an atom and electrons and the nucleus and protons and neutrons inside the nucleus? If you want to do experiments and bang atoms together and see what comes out, being able to visualize charged particles traveling through your experiment was a game changer. They could now say, if they applied a magnetic field, they could now say, well, we definitely have this type of particle and it's bending to the left, so the laws of physics tell us that that's a negatively charged particle, and this one is bending more, so the mass or the charge on this one is different to the mass or the charge on this one. You can start doing physics if you can start to see where the particles are traveling through the cloud chamber. So this completely changed the way particle physics was done in the early part of the century. And for that reason, in 1927, he was awarded the Nobel Prize in Physics for, quote, the most original and wonderful instrument in scientific history. That's quite a citation for any piece of scientific equipment. That was really a game changer. So it told us very little about Brockenspectors and clouds. It told us an awful lot about particles. And over the years, that original 1911 version has morphed somewhat into this version. That one, I'm not sure how much it costs. This one costs about £35 if you want to build one in your kitchen and look at subatomic particles for yourself. I'm not going to talk about the details of this construction, but this is what we're talking about. That's the cloud chamber seen as a section. That's what it looks like on the front here. About 6 inches or 15 centimeters or so tall, with a glass cylinder, 10 centimeters diameter, 10 centimeters high, roughly speaking. A mug warming coaster on the top, powered by a USB, is enough to generate temperatures up there of about 35 centigrade. If you put alcohol into that sponge gets warm, the alcohol evaporates, and with a little fridge unit at the bottom, a little refrigerator, that unit is bought from Amazon for about £15 or so. You get warm at the top, cold at the bottom, so clouds start to form, and just before they hit the plate, that's where you're sensitive to cosmic rays being visible in that cold plate by looking down from the top if you illuminate it from the sides or from the back. So let's go back to the cloud chamber. Perhaps it's playing ball, perhaps it isn't. It looks like it's still working. Whether or not we'll see anything interesting, I'm not going to keep on this for the next 10 minutes, but you notice a track from the left-hand side of an electron. We'll just wait a few more seconds and see if anything else interesting shows up. But of course, if you're waiting for something, it very rarely does show up on demand. I'll give you 10 more seconds, then I'm done with you. It's still working. I can still see the drizzle. We just don't have any interesting cosmic rays coming through just at the second. Oh, come on. There's one, a nice one coming through at the end there. Thank you. So let's go back to PowerPoint. So again, just in case it wasn't playing ball, here's a video I made quite a few months ago showing individual, that was an electron, that was a proton. It was a very energetic proton coming through. Over a period of time, you see quite a few tracks. I took a video for about an hour and then ran through and picked out all the interesting tracks I could find, bumped up the contrast a little bit to make them easier to see, and you see that you can get over a period of many minutes, you can see a huge number of tracks. The very bright protons here, it's difficult to see the straight muons because there's so many wiggly electrons on top, it tends to make it all very confusing. But that's just an indication of how many hundreds of tracks you can see if you're prepared to wait quite a few minutes. So we've been talking about seeing things at ground level. with a Geiger tube, Geiger-Müller tube, or a cloud chamber. But if we're interested in what's happening in terms of the top of the atmosphere or beyond the top of the atmosphere, what is it that's coming in and actually hitting the Earth? Well, cosmic ray experiments have actually been done for quite a while, since no later than Voyager. They might have started a little earlier than that, but certainly I know that Voyager 1 and Voyager 2 carried cosmic ray detectors. There it is at the top there on one of the arms. They were interested in knowing what is the flux of cosmic rays, assuming we could measure them close to Earth. Does it change throughout the solar system? Does it change in the neighborhood of Jupiter and Saturn? And if we go beyond Jupiter and Saturn and leave the solar system, does the flux of cosmic rays change in any meaningful way? Back in 2012, Voyager 1 detected a change in the cosmic ray flux, and it was determined that that change in cosmic ray flux signified the fact that Voyager had left the solar system. Voyager 2 is traveling at a different speed. Remember, Voyager 1 went to Jupiter and Saturn. Voyager 2 continued from Jupiter and Saturn onto Uranus and Neptune, and it didn't get a gravity assist from Neptune. It actually slowed down as it passed Neptune because there wasn't anything it was particularly interested in going to beyond that. So Voyager 2 has taken a little longer to leave the solar system, so it took until 2018 before Voyager 2 was deemed to have left the solar system. And that was based on cosmic ray flux. The flux from the sun, relatively low energy particles, suddenly took a dive on a particular day, and the flux from high energy particles, which were deemed to be coming from the rest of the galaxy, seemed to take an upturn. On that particular day, they said that is the day that Voyager left the solar system, because there was a sudden change in cosmic ray flux as measured by its cosmic ray detectors on board. We also have cosmic ray experiments on the ISS. This thing in the bottom right there is a cosmic ray detector. It's called the alpha magnetic spectrometer. To get the size, you can see the astronaut in the top left there. The astronaut isn't doing anything. They just happen to be in the background, and it just gives it scale. It's basically a large detector. It's not really a cloud detector. It's a large detector which can detect the passage of cosmic rays through this large volume, many meters cubed. How do we go about professionally measuring secondaries on the ground? We don't have a whole load of homemade cloud chambers dotted around the world to measure cosmic ray flux at the ground. One of the biggest cosmic ray observatories is the Pierre Auger Observatory in Argentina. Again, this is an artist's impression. If we get a shower of secondary particles, they hit a whole load of detectors on the ground. But this shower could be huge. So you need to spread your detectors over a huge footprint if you want to catch a reasonable fraction of this air shower. Now, I'm sure your geography of Argentina isn't that good, but they wanted to take a very large area in the desert that wasn't being used for anything else and spread huge number of detectors over a large area. And a large area in this context means an area the size of Luxembourg. That gives you an idea of just how big this detector is. A huge number of these water tanks. How do these water tanks actually allow you to detect cosmic rays? It's not working on the same principle as a cloud chamber. There's a different principle that allows you to detect the passage of a very energetic particle if it passes through a material which could in principle be air or water or even frozen water, i.e. ice. And the principle is, just like when you have a supersonic aircraft flying through the air, if the aircraft is flying faster than sound, in other words, if the aircraft is flying faster than the air can get out of the way, you end up with a sonic boom. You get a shock wave, which we would call a sonic boom. The same would happen with light. If a particle can travel through a medium faster than light can travel through that medium, and that's possible, remember, nothing can travel faster than light in a vacuum, but if light is slowed down as it travels through the air or through the water or through the ice, then it's possible for a particle to actually go faster than light through that particular medium. And just like we get a sonic boom when that happens with an aircraft, we get the photonic equivalent of that. We get a photonic shockwave, a photonic boom. So we can see the passage of particles by looking for a flash of light if those particles are traveling fast enough. And here's a little video that talks about that. If a particle is coming in fast enough, it can produce a shower, a cascade of high energy particles that might be moving faster than light in the air itself. and hence you get a photonic boom as this air shower develops. It's called Cherenkov radiation or Cherenkov light. It's blue and it's spectacular. This is very slowed down. The actual flash happens in about a billionth of a second. But if you have a telescope, and there's a set of telescopes in the Atacama Desert and another set of telescopes in the Canary Islands, these telescopes are not looking for the source of cosmic rays, they're looking for the blue flash as the particles come into our atmosphere. So there's a whole load of telescopes, and they have very sensitive electronics that are capable of detecting a flash, even though that flash only lasts for a fraction of a second. A whole load of telescopes are being built. They're not all there yet, but a whole load of telescopes are being built in the Canary Islands and in the Atacama Desert, in the two hemispheres, to try and give us the widest coverage possible. And remember, they're not looking to see where did that particle come from. They're looking for, can I see a blue flash? And if I see the blue flash from a number of different telescopes, then maybe I can figure out where that air shower originated. In other words, where did that original particle actually come from? You don't need to have air, you don't need to have water. It's water in the Pierre Auger Observatory, it's air in the Cherenkov telescope. Another option is you go to the Antarctic, and there's the Ice Cube Laboratory sitting on top of the Antarctic ice pack. There's the Antarctic bedrock quite a few kilometers below. If you're having trouble with scale, there's the Empire State Building, and there's the Statue of Liberty. So we have quite a few kilometers of ice, and they've instrumented this by drilling down and putting a whole load of photodetectors, like a string of pearls, thousands of them, in a cube of ice that is 1 kilometer by 1 kilometer by 1 kilometer. The largest ice cube in existence that we know about. It is literally 1 kilometer cube. So there's a sensitive area there of 1 kilometer cube. And if a particle comes into that 1 kilometer cube, if it's traveling fast enough, if it's traveling faster than light can travel through ice, then you'll get a blue flash. And if you get a blue flash, you then see which particular detectors light up and tell you they've seen the blue flash, and using the geometry of where those detectors are, you can work out that particle must have come from that direction. So in principle, you can trace back and start to find the origin of these things. So what have we found so far? What are the sources of these sometimes very energetic particles? And can we understand how they get, some of them, so much energy? Just as a little bit of an aside, we are almost at the point of the 100-year anniversary of Edwin Hubble saying the Milky Way is not all there is to the universe. On looking at these odd spiral nebula in the sky, he basically said, by looking at various variable stars in these weird nebula, we have come to the striking confirmation that these nebula are not within our own Milky Way galaxy. They are galaxies in their own right. They are millions of light years away. They are not only thousands of light years away within our own Milky Way. That was published in November 1924, so it's only a few weeks before we have the 100th anniversary of that revelation. So that was the nail in the coffin of the great debate in the 1920s that was trying to decide whether the spiral nebula were small solar systems in formation within our own Milky Way, or whether they were galaxies in their own right beyond the Milky Way. That was the nail in the coffin that proved that the universe is much, much, much bigger than we first appreciated. The entire universe isn't just the Milky Way. The Milky Way is only one of trillions of galaxies. So the scale of the universe changed almost overnight thanks to that discovery. So we can rephrase the question, not where do they come from in terms of which bit of the Milky Way do they come from. The important question, now that Hubble has told us that this paradigm shift is that the universe is full of billions, if not trillions of galaxies, is, are the sources of cosmic rays within our galaxy, or are they extragalactic? Are they coming from other galaxies outside our own? Well, some people have said, well, the only things energetic enough to actually produce very energetic charged particles that can rain down on the Earth and produce all of these showers, They must be supernova. Surely when a star goes to the end of its life, it produces a shock wave. Maybe that shock wave can accelerate particles and accelerate them up to very high speeds, nearly at the speed of light. Well, maybe they can, but theorists aren't too sure. People have, I'm not going to explain this picture on the right. People say maybe an expanding shock wave can actually accelerate particles in ways we don't fully understand. Some people say yes, some people say no. There is no consensus at the moment to exactly what mechanism might accelerate particles to very high energies. People have said, well, it might not be supernova. Could it not be the jets that are produced in supermassive black holes? We now know that supermassive black holes exist at the centers of lots of galaxies, possibly every galaxy, and many of these supermassive black holes produce jets, which are very energetic and sometimes spread for thousands, if not millions of light years out from the black hole. Maybe those energetic jets might be responsible for accelerating charged particles that ultimately produce the cosmic rays that we observe. The bottom line is we really don't know. So the question is, well, surely we should be able to pin that down. Can't we simply look at a whole load of showers and work out where they came from? Shouldn't that be easy? If we see enough showers on the ground and we pick up the secondaries and work out where they came from, or look at the way the particles are traveling through the ice in the ice cube experiment, can't we just backtrack by geometry and say, well, they appear to have come from that galaxy there? What's the problem with that? Surely that's simple. Well, unfortunately, yeah, not so simple. Mainly because we're dealing with charged particles here, and charged particles are deflected by a magnetic field. And unfortunately, magnetic fields are pretty much everywhere. We know that the Earth is surrounded by a magnetic field, and we know that relatively low energy particles can end up spiraling around the Earth's magnetic field lines, which is why they end up getting channeled to the North and South poles and give us aurora every once in a while. So we know that's a problem. Can't we sort of say, well, let's work out where the magnetic fields are, and then we can sort of correct for the fact that the particles are being deflected somewhat? We know how to work out where magnetic fields are in the laboratory. We just use iron filings, and then we say, yep, there's the magnetic field lines of that particular bar magnet. Surprisingly enough, we can do something very similar to our own galaxy. If we look at, for instance, the background cosmic radiation picked up by the Planck, some of that radiation is polarized because of dust, and dust tends to be not just a uniform agglomeration. It tends to be a very irregular shape, and these irregular shaped objects will tend to align themselves in the magnetic field. So if we look at the polarization of light scattered by these dust grains, we tend to map out something akin to the magnetic fields of the Milky Way. So it is possible to get a handle on the Milky Way magnetic fields, but unfortunately it's really complicated. And even if we could do it for the Milky Way, how on earth do we work out what the magnetic field is between galaxies? We just don't have the wherewithal at the moment to figure out if there are magnetic fields out there, how big are they, and what do those magnetic fields look like? They're not going to be anywhere as neat and tidy as the magnetic field of the Earth. Even the magnetic field of the Milky Way is complicated enough. The only possibility we have is to say, well, we know from physics that if a particle bends in a magnetic field, if it's a really energetic particle, it shouldn't bend much. So if we want to have a chance of saying that's where they came from, we need to choose those particles that are really energetic, because then at least we might be able to trace back to a particular point in the sky. There's no point in looking at the not so energetic particles, because we know that they would have been deflected all over the place, and we have no chance of telling where they actually came from. And just to give you an idea of scale, physicists use an energy unit of electron volt. An electron volt is just the energy of the light hitting my hand. In other words, visible light, visible photons of light, have an energy of 1 eV. Let's not worry about why we use that silly unit. If we go to something 1,000 times more energetic, we get to the energy of X-rays. If we go to something 1,000,000 times more energetic, we get to the alpha, beta, gamma particles of radioactivity that we were talking about earlier. But we have to go to 10 to the 9, a giga or a tera or a peta, 10 to the 15, 10 to the 18. We have to go to much higher levels to get to the levels at which cosmic rays are hitting the Earth. So you might say, okay, let's just concentrate on the really energetic ones, because those are the ones that shouldn't be deflected by a magnetic field. Just for scale, just for knowing where we are, The Large Hadron Collider is currently sending things around at that sort of energy, a few tera eV. And if they build another particle accelerator in Switzerland or France, the Future Circular Collider, that's where its energy will be. Still a long way short from the most energetic cosmic rays which are hitting the Earth. In terms of how many we might expect, the flux of particles as a function of energy, you notice that the more energetic they are, the less likely we are to see them. That's just as well, otherwise we'd be pulverized by really high energetic stuff. We think the lower energy ones are probably from the sun, the middle energy ones are probably from the galaxy, and the higher energy ones are probably extragalactic. But that's just an assumption. We haven't got any positive proof of that just yet. In terms of the low energy stuff, there were lots of these particles hitting the Earth, 1 for every square meter of the surface atmosphere of the Earth per second. The higher energy stuff, 1 per square meter per year. But the really, really, really high energy stuff, 1 for every square kilometer per year. That's going to be tricky because there aren't many of those coming in, the so-called ultra-high energy cosmic rays. But those are the ones we want to concentrate on if we want to be able to backtrack them to their origin. This was one of the most energetic cosmic ray events ever to have taken place, the Amaterasu event. It was picked up by detectors in Utah, USA. It was reported in Astronomy Picture of the Day, December of last year, and it was actually looking at data that was taken a couple of years earlier. And this was one of the most energetic events that had ever been seen. And by the way, the Amaterasu event should not be confused with the tiramisu event, which is what they had afterwards when they celebrated seeing this particular thing. So if they are really high energy, then surely they shouldn't be deflected by magnetic fields in the Milky Way, and we should have a chance of tracing them back. And this is what they've done with the handful of different events that they have seen so far that are really energetic. We're talking the right-hand end of that little scale I was showing you before. Much, 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 much more energetic than the particles in the Large Hadron Collider, for instance. So they did precisely that. They took all the data they could get from this array, they figured out where this Amaterasu particle was coming from, and they traced it back into the sky. And they found that the direction points to, pause for dramatic effect, nothing. They could not identify anything interesting. There was no obvious supernova remnants. There were no obvious galaxies with supermassive black holes in the direction pointed to by the Amaterasu event. So that means if there's no supernova and no supermassive black holes that appear to have produced that cosmic ray particle, there's a couple of possibilities. Either magnetic fields are much stronger than we think, and it has actually deviated the course of this particle, so we can't just trace back, it actually came from somewhere else. Or supernova and supermassive black holes are not the source. Maybe there's something else out there which is energetic enough to accelerate charged particles, but presumably doesn't produce an awful lot of light. Otherwise, we would have seen them. So the origin, the cosmic origin of cosmic rays is still a little bit of a mystery. My time is nearly up, so let me finish just by giving you an idea of just how energetic some of these particles might be. The Amaterasu event was thought to be the second most energetic thing that's hit the Earth since we've been measuring these cosmic ray events. The most energetic particle that was ever seen to hit the Earth was called the oh my God particle, because when the scientists saw it, they genuinely could not believe that any particle is capable of having that much energy. And remember, in physics, we can say either energy or we can talk about how close to the speed of light is it traveling, because as you get closer and closer and closer to the speed of light, it must have more and more energy. So high energy means close to the speed of light. And we can estimate, or at least we can convert the energy as determined by the experiment into, well, what was its speed? As a fraction of the speed of light, how fast was this particle going? And it turns out it was going 99.999999, not done yet, 999, still not done yet, 999, we're getting there, 999.995% of the speed of light. That's its calculated speed based on its energy. How does anything end up going that fast? That is still one of the biggest mysteries in astrophysics as to what it is that produces these things. And in order to get some attempt to visualize, other than just counting how many nines there are in there, here's a way of visualizing just how fast this particle must have been traveling. Let's imagine, hypothetically, a race between the most energetic cosmic ray that we've been talking about, a particle, a positively or negatively charged particle, a race between a cosmic ray particle and a photon. Let's imagine this is done in a perfect vacuum, so we know the light is going to be traveling at the speed of light. And we're going to have a racetrack which is 100,000 light years long. So in other words, roughly the size of the galaxy, give or take. They're going to start at exactly the same time. Now, we know nothing can go faster than light, so the light is going to win this race. It can't be otherwise. The cosmic ray is traveling almost at the speed of light, but the light is going to win. The question is, when the light crosses the finishing line after a race over 100,000 light years, how far behind it is the cosmic ray? That's one way of visualizing how fast it's going. So when light crosses the finishing line, the cosmic ray will be behind it 5 millimeters. It'll be 5 millimeters behind it after a race over 100,000 light years. And yes, if you want it in terms of stopwatch, if I hit the stopwatch when the light crosses the finishing line and then stop the stopwatch when the cosmic ray goes across the finishing line, what's the time interval between them? After 100,000 years, the time interval will be much, much, much less than a nanosecond. So again, that gives you an idea. That's an attempt to visualize just how fast these things are going, but how? How can anything gain that much energy? Still a big mystery. Whether we'll find out, we need more air showers, more detectors to give us more possibilities, and we need more theory to tell us, well, this particular mechanism could conceivably accelerate a particle under these conditions to these sorts of energies. We haven't figured out how. We haven't figured out how the particle can travel across the universe and not lose energy on its way to us, assuming this came from many, many millions of light years away. Lots and lots of mysteries. So we know that cosmic rays, to summarize, they are accelerated somewhere, somehow, but we don't really know. Supernova and supermassive black holes are probably sources, but maybe they're not the only sources. Maybe there's something out there that we've missed. We know that cosmic rays are charged particles, therefore they're deflected by magnetic fields. We would expect the low energy ones to be very much scrambled in terms of their paths. We would hope that the highest energy ones don't have their paths scrambled quite so much, but it's not altogether obvious. Some particles make it past the protection of the Earth's magnetic field. Hitting the atmosphere produces air showers of secondary particles, and some of those secondary particles will make it to sea level. We know that some of those particles are muons, electrons, protons, possibly a few other exotic particles, but those tend to be the most of them. And those secondary cosmic rays that are the result of those air showers make clicks in a Geiger counter and tracks in cloud chambers, which is what we've been seeing and hearing this evening. So remember what you're listening to. There again is the composite of a number of different tracks in a cloud chamber. Each click signifies the arrival of a subatomic particle that might have started its journey in a supernova within our galaxy, or possibly in the jets of a supermassive black hole in another galaxy 1 billion light years away. Thank you for listening.